In this lecture, I'm going to talk about vectors. In classical mechanics, we define velocity vectors, momentum vectors, force vectors, and so on. We also define, in electricity and magnetism, electric field vectors, of course, magnetic field vectors. Now, in elementary physics, it's often something called a position vector is often defined. How is that done? Well, we take the Cartesian coordinates in space of some point, the x, y, z coordinates, and we draw a little arrow from the origin to that point x, y, z, and we call it a vector. Of course, this construction assumes we have flat space with Cartesian coordinates, and in curved space or space-time, we don't have the luxury of always using Cartesian coordinates. So in fact, in the context of general relativity, we will never define a position vector. All right? We do use coordinates, of course. We use coordinates to label points in space or space-time, but that's all they are. They're a set of labels. Coordinates are a set of labels for points or events in space or space-time. All right, for example, if we have our space-time coordinates, I don't know, t, x, y, z, or we could use other letters, alpha, beta, gamma, delta, whatever they are. All they are, they're just simply a tuple, a set of values that are in one-to-one correspondence with the points in space-time. And we do not define this as a vector. There's no sense in which these labels form a vector. So not a vector. Now the standard notation for the collection of coordinates is x mu. So whether the coordinates are t, x, y, z, alpha, beta, gamma, delta, we collect them together into a single symbol x with a superscript mu, where this index mu ranges over 4 different values corresponding to the 4 different coordinates. Okay, and usually in space-time context, we let the 4 different values of mu be 0, 1, 2, and 3. So in this example, x superscript 0 is just another notation for t. x1 is another notation for x, this coordinate. x2 is another notation for y, and x3 is another notation for z. Again, this is not a vector. It's simply a set of labels labeling points in space-time or events in space-time. So how do we define a vector in curved space-time? Well, let's begin by looking at the example of a velocity vector. So here's a space-time diagram, and there can be 4 dimensions here, but I'm only drawing 2 of them for simplicity. Let's take a world line that's time-like. So here's a time-like world line. So it's time-like, meaning at every point the curve lies within the future light cone of that point. So this is the path that a physical observer or particle could take. All right, and we know how to describe the world line. We parameterize it. So this is lambda equals 0, lambda equals 1, 2, 3, and so forth. All right, and to specify the world line, we then give the coordinates as functions of this parameter lambda. So the coordinates with our new notation are x mu. So we give this set of functions x mu as functions of lambda to specify the world line. So this is the world line. Now, given this set of functions, we can differentiate them with respect to lambda. So we can compute the derivative of each of the x mu's with respect to lambda. Is this the velocity vector? Well, the answer is no. First of all, notice this doesn't really have any direct physical meaning. And it has no direct physical meaning for two different reasons. First of all, these coordinates x mu are arbitrary. There's simply a set of labels on space-time, and there's lots of different ways we can put down those labels. So depending on how we put the labels down onto the space-time, we'll get different expressions for these derivatives. And the second reason that this has no direct physical meaning is because the parameter lambda is arbitrary. Really, the only restriction on the parameter lambda is that it should be monotonic, so that there's a one-to-one correspondence between parameter values and points along the world line. Other than that, this parameter lambda is arbitrary. We can improve our situation by replacing this arbitrary parameter with proper time. Call it tau. All right, proper time is a physical parameter. It's the time as measured by a clock that's carried along the world line. Okay, so that has physical meaning, and we can parameterize our curve, our world line, with proper time. So this is the world line. And then we can differentiate this with respect to proper time. This still has no direct physical meaning because the coordinates are arbitrary. So how do we remove the arbitrariness in the coordinates from this expression? Well, the way we do that is by stripping away the x mu in this expression. So we define the velocity vector as the derivative with respect to tau. So this is, mathematically speaking, this is a directional derivative operator. This is one of the most important conceptual steps you'll have to take in learning general relativity. At least for me, it was very important and a very difficult concept. A vector is a directional derivative operator. So what does a derivative operator do? Well, a derivative operator acts on functions. So let's take our vector, our derivative operator d by d tau, and let it act on a function of space-time. So this would be a function that has a different value at each point in space-time. So it depends on the space-time coordinates x0, x1, x2, and x3. And by the way, sometimes I'll denote a function like this as f of x mu. Or even for simplicity, I might write f of x, with the understanding that this x stands for all of the space-time coordinates x0 through x3. So now let's let this operator act on this function of space-time and use the chain rule. So d by d tau acting on f is equal to partial of f with respect to x0 times dx0 d tau plus partial f with respect to x1 dx1 d tau partial f with respect to x2 dx2 d tau and partial f with respect to x3 dx3 d tau. All right, we can write this more compactly as the sum over mu from 0 to 3 of partial f with respect to x mu dx mu d tau. Of course, we can write these two factors in either order. We could also write this as dx mu by d tau times partial f with respect to x mu. All right, so this applies for any function f. So in particular, let's abstract this by stripping off the f, and we find d by d tau is equal to the sum over mu from 0 to 3 of dx mu d tau partial with respect to x mu. So what we have here is a linear combination with coefficients dx mu d tau of these derivative operators. So these derivative operators these are directional derivatives along the coordinate lines x0, x1, x2, x3. Directional derivatives along the coordinate lines. Okay, these form a set of basis vectors associated with the coordinate system. So these are the basis vectors. Associated with the coordinates x mu. And notice these coefficients, this is just our tentative expression for the velocity vector when we use the proper time as the parameter along the world line. So what these are really the components of this vector in this basis. So dx mu d tau, these are the components of the vector d by d tau in the coordinate basis d by dx mu, or partial with respect to x mu. In this context, I don't make a careful distinction between the symbol d and the partial symbol. The meaning is always clear, whether it's written as a d or as a partial. Let me summarize what we've found. We have a world line, and that world line is parameterized by proper time. That's the time the time read on a clock that's carried along the world line. And the velocity vector is this operator actually it's a bunch of vectors, one at each point along the world line, and we sometimes, just like in elementary physics, we draw those velocity vectors as little arrows. Right? dx mu by d tau, these are the components of the velocity vector, with emphasis on the word components. The components of the velocity vector in the coordinate basis. And the quantities d by dx mu, these are the coordinate basis vectors. So these are the directional derivative operators along the direction of the coordinate lines. Let's take a look at a specific example. Consider flat space-time in 2 dimensions, Minkowski coordinates, so the line element looks like this. And we'll take the world line to be t of lambda equals lambda, x of lambda equals the square root of 1 plus lambda squared. Now we need to parameterize this world line in terms of proper time. So proper time is square root of minus ds squared, so that would be dt squared minus dx squared. So let's compute, well, dt is just d lambda squared minus dx squared. Dx is the derivative of this, that's 1/2 1 over the square root of 1 plus lambda squared, times the derivative of 1 plus lambda squared is 2 lambda d lambda. All right, we have a common factor of d lambda squared in both of these terms, so we can pull that out of the square root as a d lambda. And under the square root, we're left with 1 minus lambda squared over square root of 1 plus lambda squared, so that's 1 plus lambda squared in the denominator. And now we can combine these two terms. We have 1 plus lambda squared minus lambda squared divided by 1 plus lambda squared. These lambda squareds in the numerator cancel, and we're just left with d lambda divided by square root of 1 plus lambda squared. That's d tau. We can integrate this. And the integral of 1 over square root of 1 plus lambda squared is inverse hyperbolic sine of lambda, arc sinh lambda. And of course we can add a constant to that, since this is an indefinite integral. But this constant, notice it just shifts where we choose tau equals 0 along the world line. So just for convenience, let's just set that equal to 0. All right, so this tells us that lambda is hyperbolic sine of tau. And now if we return to our expressions for the world line, we see that t is sinh tau, and x is 1 plus sinh squared, that's cosh squared, take the square root. This is cosh tau. So in terms of proper time, our world line is sinh tau is the t coordinate, and x of tau is cosh tau. The velocity of this world line is d by d tau. We can expand this using the chain rule. This is dt by d tau d by dt plus dx d tau d by dx. dt d tau, that's the derivative of t, is cosh tau. So that's cosh tau d by dt plus the derivative of x is sinh tau d by dx. So these quantities, cosh tau and sinh tau, are the components of this velocity vector in the coordinate basis. The coordinate basis vectors are d by dt and d by dx. All right, so we can write, if you like, the components dx mu by d tau are cosh tau, comma, sinh tau. These are the components of d by d tau. Keep in mind that d by d tau is not just a single vector, it's a vector at each point or each event along the world line of this particle. And likewise, these are the components of all of those vectors, one vector for each value of tau. So for example, if this is the world line and this is the event labeled tau equal 2, then the components of the velocity vector at that event are cosh 2, comma sinh 2. Right. And also notice that in this context of general relativity, we never want to move vectors around. Sometimes we're taught in elementary physics that vectors have no location and can be moved arbitrarily, but that's not the case. This vector represents the velocity of the particle at this event. It's not the velocity of any other particle or even the same particle at some other event. So it's attached to this point and should not be moved. Now let's consider the extension of this definition of the velocity vector as a directional derivative operator to all vectors. So let V denote a vector. So it's an operator that acts on functions. So we can expand this vector in a linear combination of basis vectors. So we would write V equals the sum over V mu d by dx mu, where mu ranges from 0 to 3 in the context of space-time. And the basis vectors associated with the coordinate system x mu are these operators d by dx mu. Now we can do this, define vectors this way for any space or space-time. So in particular, if we look at the three-dimensional Euclidean space of Newtonian mechanics, so that takes place in three-dimensional flat space. And let's define the Cartesian coordinates to be x, y, z, or xi, where I ranges over 1, 2, and 3. All right, then any vector can be thought of as a directional derivative operator and can be expanded in a linear combination of basis vectors d by dxi, where now I ranges 1 to 3. Now these quantities, the VIs, these are the components of the vector V. Let's consider a force vector F. All right, this is a derivative operator, so it acts on functions. So how do we interpret this as a force? So let's say the force acts at some point here in space. Well, this acts on a function, so let's take a function, say, call it phi. And phi is defined in the vicinity of this point. And we can draw the curves of constant phi. So let's say these are the level surfaces or curves of constant phi. Now with the line element, we can determine the direction in space along which phi changes most rapidly. All right, so let's say that's this direction right here. This is the direction in which phi changes most rapidly. And let's also scale phi such that these curves of constant phi represent actual physical distance along this direction of most rapid change. So in other words, if this is phi equals 0, 1, 2, 3, and so forth, that this actually represents 1 meter of physical distance along this direction of most rapid change. And these lines are separated by 1 meter along the dashed line here. All right, if we do that and then let our vector f act on this phi, what we get is what we would call the force in this direction of most rapid change, or sometimes we would refer to that as the component of the force in this direction. The component of the physical force in the direction of most rapid change in phi. Notice that the definition of this force vector is independent of any coordinates that we might be using. Right? So we might use, say, Cartesian coordinates, in which case we would expand the force vector as a linear combination of basis vectors d by dx, d by dy, d by dz, and write the function phi as a function of x, y, z, and then let f act on phi, and we get the component of the force in the direction in which phi is most rapidly changing. Or we could do the same calculation in terms of, say, spherical coordinates. Right? We could expand this in spherical coordinates r theta phi, r f theta d by d theta plus f phi. Well, I shouldn't have used the letter phi since I'm using phi to denote the function. I'll write the phi as a curly phi here, d by d curly phi. Okay, and we can write our function phi as a function of the spherical coordinates r theta and curly phi. And then this calculation again just gives the same physical force component in the same direction, the direction of most rapid change of the function phi. Let's take a closer look at Cartesian coordinates. X, y, z for the three-dimensional Euclidean plane. All right, now these coordinates, like any set of coordinates, can be viewed as functions on space. All right, so for example, the x-coordinate is a function that takes any point in space and tells you what the x-coordinate is at that point. All right, so in fact, we can draw the surfaces of constant x. All right, so this is the x equals 0 surface, 1, 2, 3, and so forth. And now one of the nice things about Cartesian coordinates is that they're scaled so that they give the proper distance. So the proper distance in particular along the direction in which the coordinate most rapidly changes. So x equals 0 and x equals 1 are separated by 1 meter along the perpendicular distance here, which is the direction in which x is changing most rapidly. So this is the direction of most rapid change in x. Okay, and in fact we know, because of the line element is so simple, we know that that direction is the direction perpendicular to the x equal constant surfaces. All right, so if we compute then, so this is a function on space, and we can let the force vector act on that function. So we'll let f act on the coordinate function x. And what do we have? Well, let's expand f in terms of the coordinate basis. So this is the sum from 1 to 3 of fi d by dxi acting on x. Writing this out explicitly, we have f1 partial x with respect to x plus f2 partial x with respect to y plus f3 partial x with respect to z. Now, of course, partial x with respect to y and z are 0, whereas partial x with respect to x is 1. So this is just equal to f1. So we see in this case with Cartesian coordinates that the one component of f, or the x component of f, has a direct physical interpretation as the component of the force in the direction perpendicular to the x equal constant surfaces. This component of the force in the direction perpendicular to x equal constant. So in Cartesian coordinates, the components Fi, these are the components of the force vector, the force derivative operator. These components do have a direct physical interpretation. It's physical interpretation as the components of the force in the x, y, and z directions. You might notice that I'm using the term components here in two different ways, so this is kind of a funny statement. Here, by components of f, I mean the coefficients of f when we expand f as a linear combination of basis vectors, d by dx, d by dy, and d by dz. And here the term components means the physical part of f that's in the associated direction. You should note that in other coordinate systems, for example, spherical coordinates, this statement doesn't hold true. So in spherical coordinates, the components of the force vector, f theta, fr, f theta, f phi, these are components in the sense of an expansion in terms of the basis vectors. These components are not the physical components in this sense of f in the directions of the r equal constant, theta equal constant, and phi equal constant coordinate lines. We'll just call those the r, theta, phi directions. Okay, they are pretty closely related to those physical components, and you'll see in other branches of physics the physical components are defined in terms of these quantities. But these quantities themselves, the expansion coefficients in the coordinate basis, don't have the direct physical interpretation. Before continuing, let me introduce the Einstein summation convention. The Einstein summation convention says that in any mathematical term in which an index is repeated, you must sum over the index. So sum over repeated indices. So for example, when we write the force vector as a linear combination of basis vectors, you notice that the index I is repeated. It appears twice. I is repeated. So that's our clue that we need to sum over I. So I've written the sum here explicitly, but with this convention we can write this expression as fi d by dxi, where the sum over I is implied. All right, so more generally, if we have, say, a vector in space-time, we can write it as an expansion in terms of the basis vectors d by dx mu. So this is just shorthand notation for the sum over mu from 0 to 3 in this case of v mu d by dx mu. With the Einstein summation convention, we don't have to write this sum sign explicitly, and we can shorten our expression just writing it this way. All right, so this is the expansion of some vector in terms of a coordinate basis x mu. Now, coordinates are arbitrary. We can choose coordinates however we like. So what if we have another coordinate system? Let's call the new coordinate system x mu bar. All right? Well, we can also write this same vector as a linear combination of basis vectors in this coordinate basis. So we would have some new coefficients, v bar mu, in the expansion of this vector in terms of the basis vectors d by dx mu bar. Right, so these are the basis vectors in the x mu bar coordinates. And these are the components of v in the x mu bar coordinates. Now let's take a look at one of these basis vectors, for example, d by dx bar 0. We can use the chain rule to expand this as dx0 by dx bar 0, d by dx 0, plus dx1 by dx bar 0, d by dx1, dx2 by dx bar 0, d by dx2, and so forth. All right, so this sum can be written as partial with respect to x nu with respect to x bar 0, d by dx nu. And remember, by the Einstein summation convention, this Greek letter nu is repeated, so it's being summed over. And that's the sum we see here, the first three terms of that sum. All right, so more generally, we can write d by dx bar mu as partial of x nu with respect to x bar mu d by dx nu, or we're summing over nu, the repeated index. All right, now, and again, this is just the chain rule. So if we look at v expanded in terms of the barred basis, we can write it now as v bar mu, what we had before was d by dx bar mu. We can now write this as partial x nu with respect to x bar mu, d by dx nu. All right, now what do we have here? What we have is the vector v expanded in terms of the coordinate basis for the unbarred coordinates. The unbarred coordinates x mu. And the coefficients are the components of v in this basis. So the components of v in the unbarred coordinate basis. All right, but that, of course, is what we had written down up here. Okay, so by just equating these two expressions for v, we have v mu d by dx mu is, now just repeating this, we have v bar mu dx nu by dx bar mu d by dx nu. Notice in this expression we have a repeated index nu that's being summed over, and also a repeated index mu that's being summed over. Now, when there's a repeated index and it's being summed, we can call it anything we like. We don't have to use the Greek letter nu here. We could use alpha, beta, gamma, anything we like. It's just a dummy index that's being summed over. So in particular, we could, if we wanted to, we could swap mu and nu. So in other words, instead of saying nu here and here, we could use the Greek letter mu. Instead of mu here, we could use the Greek letter nu. So this is the same thing as v bar nu partial x mu with respect to x bar nu d by dx mu. Now, one of the reasons I wanted to swap indices like that is because notice I have the basis vectors d by dx mu here, and now we have the same symbols here. So I'm going to strip off the coefficients, all right, and now the component, write the component of the vector v in the unbarred coordinate basis as this expression. This is v bar nu d by dx mu by d bar nu. All right, so if we change coordinates from unbarred to barred coordinates, this expression tells us how the components of a vector v change under that coordinate change. This is the change in the components of v when we change coordinates, or in other words, under coordinate transformation. And of course, it's not hard to show that you can also write this expression the other way around for v bar in terms of v. It would just look something like v bar mu is v nu times dx bar mu by dx nu. Let's take a look at a specific example. Let's consider flat 2D space with Cartesian coordinates. So we know the line element is dx squared plus dy squared. And let's consider the vector field v equals x plus y d by dx plus x squared over y d by dy. Now notice, by the way, this is a vector field. So in other words, it's not a single vector. It's a bunch of vectors, one vector at each point in space. So for example, at x equal 1, y equal 2, v at that point is 3 d by dx plus 1 squared over 2 is 1/2 d by dy. Okay, and at other points in space, there will be other vectors. All right, so the components of this vector in the Cartesian basis are just the coefficients of d by dx and d by dy. So the first component is just x plus y, and the second component is x squared divided by y. These are the components of this vector field. All right, let's convert this to polar coordinates. All right, polar coordinates are related to Cartesian coordinates by x equal r cosine theta, y equals r sine theta. And so converting this now, we can apply the chain rule. So first of all, x plus y is just r cosine theta plus r sine theta. And d by dx, by the chain rule, is partial r with respect to x, d by dr, plus partial theta with respect to x, d by d theta. And now for this second term, we have x squared over y, that's r squared cosine squared theta over r sine theta, times d by dy, which is dr dy, d by dr, plus d theta dy, d by d theta. Okay, to continue, we need to compute these derivatives, dr dx, d theta dx, and so forth. Now, let's remember when we write dr dx here, what we mean is the derivative of r with respect to x holding y constant. All right, so in order to compute that, we need to invert these relations. We need to write r in terms of x and y. So r is square root of x squared plus y squared. And theta in terms of x and y is the arc tangent of y over x. All right, so now we can compute the derivatives of r with respect to x holding y constant, derivative of theta with respect to x holding y constant, and so forth. All right, the results of those calculations are dr dx is equal to cosine theta, d theta dx is minus 1 over r times sine theta, dr dy is equal to sine theta, and d theta dy is equal to 1 over r cosine theta. All right, now we can insert those results in for these factors. Okay, when we do, what do we get? We have, from the first term, we have r cosine theta plus r sine theta times dr dx is cosine theta, then d by dr, and from here we have d theta dx, that's minus 1 over r sine theta d by d theta. And now for this term we have r squared over r just gives a single factor of r. So we have r cosine squared theta over sine theta times dr dy is sine theta, and d theta dy is 1 over r cosine theta. So now we can simplify this. First collect the terms involving d by dr. So this is r cosine theta plus r sine theta times cosine theta plus r. Now sine cancels the sign in the denominator. We just have r cosine squared theta. All of that times d by dr. All right, and then similarly we can collect the terms proportional to d by d theta. We can simplify this a little bit by noticing that there's a common factor of r cosine theta in this first term, and then we're left with cosine theta from here, cosine theta from there, that's 2 cosine theta, plus from this term we have sine theta. And all that's times d by dr. And then we also have the term proportional to d by d theta. So the components of v in this coordinate basis, the polar coordinate basis, the r component is r times cosine theta times 2 cosine theta plus sine theta. And the theta component is whatever this expression turns out to be. All right, so that's the vector field expressed in two different coordinate systems. Let's consider this vector field acting on a function. Let's take the function to be, say, x squared plus y squared. All right, we'll have to remind ourselves this was x plus y d by dx plus x squared over y d by dy. So v acting on f is x plus y. The derivative of this function with respect to x is 2x plus x squared over y. The derivative of this function with respect to y is 2y. So that simplifies a bit to 2x squared plus xy plus 2x squared from this term, which is 4x squared plus 2xy. All right, so at each point in the space, the vector acting on this function gives this number. Now, the notion of a vector acting on a function is independent of the coordinates we use, so let's compute this v acting on f in polar coordinates. All right, in polar coordinates, we have the component VR is r cosine theta times 2 cosine theta plus sine theta, d by dr, and that's plus some coefficient that we didn't actually compute, d by d theta. All that acting on the function, and now the function is just r squared. So this is acting on r squared. All right, so actually the derivative with respect to theta of r squared is 0, so this term goes to 0, and we're left with r cosine theta times 2 cosine theta plus sine theta times d by dr acting on r squared, which gives 2r. Right, so this is 2r squared cosine theta times 2 cosine theta plus sine theta. Okay, and if we compare that to the result that we got before, we can see it should be the same thing. Let's simplify this, bring the 2 inside, that gives 4, then r cosine theta is just x, and we have 2 factors, that gives x squared. And for the second term we have 2 r cosine theta times r sine theta, that's 2 times x times y. So we indeed get the same result, whether we use polar coordinates or Cartesian coordinates. Let me finish with a quick comment on terminology. If we have a vector v, this is a derivative operator. The precise term is it's a contravariant vector. Although we'll often leave off the word contravariant and just refer to it as a vector. So for example, d by d tau is the velocity vector, and it's a contravariant vector. The coordinate basis vectors are contravariant vectors. There's one vector for each value of the index mu. And when we expand a general vector in terms of a coordinate basis, these coefficients are the components of what is strictly speaking a contravariant vector. And we'll always write the index on a contravariant vector, on the components of a contravariant vector, as a superscript, never as a subscript. When we write a symbol with a subscript index, it means something else, as we'll see later in the course. All right, now, later on, when we really start working with the Einstein equations and start working out properties of black holes and cosmology and so forth, we'll mostly work with components of vectors. So we mostly work with vector components, not the vectors themselves. So at some point, I'm sure I'll become careless and I'll refer to v mu as the vector. But of course, v mu is not really the vector. V mu is a set of components. They're the components of the vector in a coordinate basis.